Okay, guys, notice we have a question that says solve using Kirchhoff laws. So we observe, okay, we have several supplies, one, two, three, four supplies in three loops. So it's a Kirchhoff law question. First thing we have to do, remember, is we have to select uh, a loop current. And it's random. It doesn't matter which direction I choose. So I'm going to say this is I1, IA if you like. I'm going to say this is IB. And I'm going to say that's IC. All right. And these are random currents. It doesn't matter. I could have chosen any direction I wanted. The next step is to put in our voltages. For the voltages, remember we have a convention that says voltage acts in the direction of the high potential. So we have a voltage here. That's 20 volts. We have a voltage going up like this. That's 6 volts. We have one coming down. That's 10 volts. And we have this one over here going this way. That's 12 volts. All right, so that's done. The next phase is we have to put in the various voltage drops across each of the components in the circuit. In this case, we only have resistors. Now, look at IA. IA is moving around in a clockwise direction. So, through this 2 ohm resistor, IA is going from left to right. Therefore, the voltage drop must be going like that, from right to left. IA is going up, so the voltage must be acting down. To this 3 ohm resistor, IA, if it's going clockwise as we say, the voltage, the current is going down, the voltage must be going up. IA is going this way, from right to left, therefore the voltage must be going this way. Similarly, this voltage must be going this way. That's loop 1. But we have to do that for all the loops. So we come to IB. IB is going clockwise again. It's going up through this 2 ohm resistor. Therefore, the voltage must be acting down. IB is going clockwise through this second 2 ohm resistor. It's going from left to right. Therefore, the voltage must be going from right to left. Always opposite the direction of current flow. In this 1 ohm resistor, the current is coming down, therefore the voltage must be going up. In this 2 ohm resistor, similarly, voltage is going down, therefore the current is going down, therefore the voltage must be going up. I notice I missed one here. This 1 ohm resistor has a voltage going in this way. Okay, now moving across to IC. IC has a voltage in this 1 ohm resistor going, IC is going up, therefore that voltage must be acting down. IC is going up through this 2 ohm resistor, therefore the voltage must be acting down. IC is going from right to left, therefore the voltage must be going from left to right through this 1 ohm resistor. IC would be coming down, therefore its voltage must be going up in this resistor. And IC will be going from left to right, so the voltage must be going from right to left, always in opposition. Now we have to be careful to make sure we didn't miss anything. So here we have it right, that's correct, that's correct. Okay, we have 2 because 2 currents flowing through it, and this is 2, right? Same thing over here. Alright, so just make sure that we have all our voltages acting in opposition to the current. So travel along in the direction of the current, yes, 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 yes. This is good. Traveling around, yes, yes. So we have all our, so we're now ready to set up to work this Kirchhoff question. We now have to apply Kirchhoff voltage law to determining the voltage around each loop. So we're going to now apply KVL to loop A. Pick a convenient point to start. I like to start at the supply. And it doesn't matter what direction I go in direction of the supply. So I have 20 plus 2IA plus 4IA plus 2IA and I have another voltage here which is 2IB, but we're going against it. So I'll say minus 2IB. So you see this one is positive and this one is negative. Continuing, I have 4IA plus 4IA, and then I have another voltage in that same 4 ohm resistor going against it, so I'll say minus 4IC, that's B. Then continuing, I have 3IA continuing, I'll have 1IA and I'm back to the supply. So that's equal to 0. That's Kirchhoff law, say all the voltages around a closed loop must add to give 0. Now I'll do a quick check to make sure I have all voltages accounted for. So starting from the 20, 1, 2, 3, 4, 5, 6, 7, 8, 9 voltages. 1, 2, 3, 4, 5, 6, 7, 8, 9 voltages. So that's correct. Now I wrote it this way because I want to fit it on. I want it to fit on the screen. You can write it anyway convenient. Just make sure you have your signs correct. So now I'll gather up all the IAs, IBs, and ICs and see what I get. So gathering these up, I have 20 is equals to 4, 6, 8, 12, and 4, 16. 16 IA minus 2IB minus 4IC equals 0. I said something wrong. That's not equal. That's plus. So let me erase that. Yeah, that's plus. So it's 20 plus. Now I want this thing to be written, look like an equation. So I'll take that 20 across to the other side. So my equation 1 will be 16 IA minus 2IB minus 4IC equals to negative 20. And that is my first equation. Now I have to go and do the same identical thing for the other two loops. So let's go to loop B. So same idea. Pick a starting point, any convenient starting point. I always like to start at a voltage. So this becomes 10 volts. Let me use a different color. Here, this becomes 10 volts plus 2IB plus another 2IB minus 2IC plus IB minus IC plus 6 plus 2IA minus 2IA and there is a voltage here which I missed, and that's plus 1 IB. Equal to 0. So let's go do a check. I have, starting from the 10 volt supply, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all accounted for. Now, same procedure. Gather all the like terms and write it out like a nice mathematical equation. Gathering up all the terms, like terms, and writing it out like a normal linear equation. Like terms, looking at the constant terms, we have 10 and 6 is 16. 16 plus 2IB, 4, 5, 7, 8IB. ICs, minus 2, 1 minus 3 ICs, yes, minus 3 ICs, and IA minus 2 equal to 0. Again, I want A's, B's, and C's, so I'll say minus 2 IA plus 8 IB minus 3 IC equals to negative 16. And that is my second equation, sorry. We now have to proceed to do the same operation with IC loop 3. There's no space to write, so what I'm going to do, I'm going to cut this part of the circuit out, copy it later down, so that we can look at it and write at the same time, which I did here already. So let's go ahead and write out the loop equations for this loop. Again, picking a convenient place to start. I'm going to start here. I'm going to say 12, going in this direction, 12 plus 5, 5 IC plus 4 IC minus 4 IA. Remember, IA was flowing in that first loop. I cut it out, so it's not here. Plus 4 IA minus 6 volts. See, we're going against that arrow, so it's a minus. It's minus 1 IB plus IC minus 2 IB plus 2 IC plus 1 IC and we're back at the 12 volts. So that's equal to 0. I hope I didn't miss anything there. Let's check. So again, it's starting from the 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That seems to be okay. So now we go ahead and do the same operation. We gather all the like terms together. So 12 and 6 is 6. And IC is 5 and 4, 9. And 1, 10. and 313. So that's plus 13 IC. Let's go IA, minus 4 IA, and that's about it. Minus 4 IA, and IB, 1, and we have negative 1, negative, that's negative 3 IB, equals 0. Again, I want A's, B's, and C's, so I'll say minus 4IA minus 3IB plus 13IC, taking the 6 over, equals to negative 6. And that is my third equation. The next step I have to do now is put these three equations side by side, arrange them in a manner which I can solve, and proceed to solve. Now, the next stage is for you to solve these equations. I have a calculator that allows me to solve linear simultaneous equations with 3 variables, but there are many apps online that allows you to solve linear simultaneous equations with 3 variables. Do a search for that. Linear simultaneous equations with 3 variables. And you enter them. They have various formats for entering them. And each of them will give you the particular format, but they will, at the click of a mouse, you will get solutions. And you'll get that IA is equals to negative 2.11 amps. 2.12 amps, sorry. IB is equals to negative 3.23. And IC equals to negative 1.86 amps. Now, interestingly, all our currents were negative. That means all the directions we assume were incorrect. That the true current is opposite to the directions we assume. So this is something we have to go back to our circuit now and make the change. But we have values for the 3 loop currents, and this is an important step. It is from this point we can now apply KIL, Kirchhoff current law, to solve for the current in the various branches. I get 1.11 amps. So that's the current Ix. So I know now that this current here, Ix, it's positive, so it's moving towards the junction. .11 amps. So that means this current is going in this direction. 1.11 amps. I'm going to do the same thing for this junction B. So just like before, I don't want to spoil what's going on here. So let me select it out and bring it down so we can work in isolation. At junction B, we say the same sort of thing. We can say that IC is moving towards junction, IA is moving away from the junction, and we want to find this current here, which we call it IY. We don't know if it's towards or away, so we can't write in anything. But we could say that IY plus IC minus IA is equal to 0. Now I have my IC is 1.86. So 1.86. IA is 2.12, so plus a negative 2.12 plus IY is equal to 0. Again, I'll put that in my calculator and get a quick results for you. So IY is equals to negative 0.26. On this side, take it across, I get 0.26 amps. So IY is a positive, that means it's entering the junction, so it's coming like this, and it's 0.26 amps. Going to my main circuit, I could put it here, 0.26 amps. Now I'll do the same exact thing to this junction C, and I'll find the current coming down this middle wire. Okay, so following the same pattern I did before, I will isolate this because I don't want to introduce confusion into my main circuit. There it is. I'll call that IZ going up. So IZ, I don't know what direction it is, but I'll call it IZ. Following the same rules, I know I have IB towards the junction minus IC away from the junction. These two I'm sure about. IZ I don't know. So I put plus IZ is equal to 0. Values. IB is equals to 3.23. 3.23. IC was 1.86 plus negative 1.86 plus IZ is equal to 0. Again, chucking this into my calculator. On the left hand side, I'll get 1.37. Taking it across, I get that IZ is equals to negative 1.37 amps. That tells me, negative sign tells me it's moving away from the junction, so I know it's going up like that. Taking that across to my main circuit, I know that it's going up here. And that's what I got there again, 1.37. 1.37. So looking at what I have here, I've solved this circuit completely, because now I have the currents passing through every single resistor or battery. Now, let me see if there's any unusual thing here. No, there's nothing unusual. Sometimes you will find that, let's say this current was going into the positive side. As it is, right now IC is flowing out of the battery. But sometimes you may do a calculation and you'll find that the current is going into the battery. That tells you that that particular battery is on charge, it's charging. But as we have it here, none of the batteries have their currents going into them. They're actually going into the negative, coming out of the positive, which is conventional. Going into the negative, coming out of the positive, that's conventional. And there you've solved the circuit completely. At this point, if somebody asks you to find the voltage across any resistor, you just multiply the known current by the given resistor. Now, asks you to find the power, you use I squared R or V squared upon R or IV. And you can say essentially this circuit is solved.